So one thing you can do to improve the efficiency of power delivered to a load is called power factor correction. There are certain values for voltage regulation and efficiency that are good for delivering power, but when you don't have good values, you do something called power factor correction. So that's what we're going to talk about today. The power factor is a fraction of the apparent power that is turned into real power. It does not have a dimension because we know the power factor is just the cosine of theta V minus theta I. So it's dimensionless, but that numeric value tells you what percentage is turned into real power. It's always positive because the cosine of an even number is going to be the cosine of a real number is either going to be positive or negative, right? So since we know it's either going to be the real part plus JQ, whether Q is positive or negative, the cosine is always going to be positive. So that's why we have to use lagging and leading so that we know whether we have an inductive load, a capacitive load, or whether Q was greater than or less than 0. So just remember, Q greater than 0, inductive, means the power factor is lagging. Q less than 0, capacitive, means the power factor is leading. And this also means that theta V minus theta I is greater than 0. And this one means theta V minus theta I is less than 0. So that's what that first paragraph says. For example, in an inductive circuit, the power factor is lagging because the current lags the voltage, while in a capacitive circuit, the current leads the voltage. We have seen that the power factor is the ratio of the real power to the apparent power, and can also be thought of as the cosine of the angle between the voltage and the current. Power factor is a dimensionless number between 0 and unity, with the extreme values being a purely resistive circuit has unity power factor, a purely inductive circuit has 0 power factor lagging, and a purely capacitive circuit has power factor leading. Is it 0 though? Yeah, it would be 0. Yeah, it would be 0. So most industrial loads are magnetic, consequently their power factor is lagging, and when lagging power factors are low, several undesirable effects happen, such as increased current, requiring larger feeder conductors, lower voltage at loads, and increased loss of power. All these effects can be improved if the power factor is increased by adding capacitors in parallel with the load. Okay, so that's what we're going to do today. It's called power factor correction. And it's very important. Voltage regulation is the percentage increase in voltage when a circuit is suddenly unloaded. So let's look at an example of what this looks like. I'm telling you right now, you're probably gonna need some extra paper because I did not leave enough room for this. I did not realize how long this problem was when I put it on here. Okay, so first thing we want to do is, if the load power factor is 0.5 lagging and you have a voltage source whose feeder is 2 plus J8. The feeder is basically like the wires that are connecting the source to the load. So this is our source. This is the load, and feeder is like the wires. So that would be like if it was a power plant and you have the cables that get into your house. These are like the wires in the cable. Okay, and it supplies a load of 1 milliwatt at 10 kilovolts at 60 hertz. The element labeled CB is called a circuit breaker and is used for interrupting current. So that means that if you exceed a certain rating, in order to keep from damaging equipment, the circuit breaker would flip. Everyone's probably seen a circuit breaker in their home. Like if you drop your hairdryer in the water, God forbid your hand goes in, the circuit breaker would trip, typically in the bathroom. Has anybody ever seen a circuit breaker trip? Or am I speaking another language right now? Okay. All right, so that's what a CB is, a circuit breaker. So determine the magnitude of the supply voltage, the real power drawn from the load, and the efficiency of the transmission when you have a low power factor of 0.5, a low power factor of 0.95. So you can see how the power factor affects this. So that's what we're going to find here. So the first thing we're going to find is the apparent power, which is the real power over the power factor. What is it? Okay, so what's the apparent power? Yes, talk to me. 2 mega, but it's actually volt amperes, but you're right. Okay, so then theta equals theta V minus theta I, which is the arc cosine of the power factor. So that is going to be the arc cosine of 0.5. Theta, which is theta V minus theta I, is the arc cosine of 0.5. So what is that angle? 60 degrees, right? So our apparent power was 2 mega VA. So our complex power, which is S, is the magnitude of S and the angle of theta. So that's 2 with an angle of 60 degrees mega volt amperes. Okay. So now what about the current in the circuit? So the current I is going to equal S over V conjugate. S over V conjugate. So that means you're going to have 2 with an angle of 60 degrees divided by 10 kilovolts. And remember, this is mega VA. So you're going to divide that and then take the conjugate. 2 with an angle of 60 degrees, but that's 2 mega divided by 10K, and then take the conjugate. I'm going to go with 200. You guys are killing me. It must be Friday. 200 with an angle of negative 60 degrees. So now we need to use KVL to find the voltage at the source. The voltage at the source is going to equal the voltage at the feeder plus the voltage at the load. The voltage at the feeder is going to be 2 plus J8 times I, plus the voltage at the load is given. That's 10 angle 0 degrees in kilovolts. So that's going to be 2 plus J8 times 200 with an angle of negative 60 degrees plus 2 with an angle of 0 degrees in kilovolts. What is VS? 11.59. Did anyone get that? Okay. So 11.59 with an angle of 2.2 degrees in kilovolts. So in order to get 10 kilovolts out, I got to send 11.59 in, which is a big difference between 11.59 and 10K. So this is what happens when you don't have a good power factor, is it requires a large voltage just to get 10 on the other side. And the way we quantify this value is called the voltage regulation. The voltage regulation is the voltage for the unloaded circuit minus the voltage for the loaded circuit divided by the voltage for the loaded circuit times 100. So it's the voltage for the unloaded circuit minus the voltage for the loaded circuit divided by the voltage for the loaded circuit times 100. Ideally, you want to keep this value under 5%. So if we do this, we get 11.59 minus 10 over 10 times 100. 11.59 is the source. minus 10 is the voltage at the load divided by 10 times 100. So this equals 15.9%. Ideally, we want this less than 5% for continuous operation, or 10% for temporary conditions. Okay. So 15.9 is too high. That's the point here. So this is what we use power factor correction for, is to get the power factor to a value that works better than this. The other way that we rate a system is called efficiency. Efficiency, N, is equal to power at the load divided by power at the source times 100. Oops, I'm out of room. So we need to find the power at the source. And I'm going to just squeeze this in here somewhere because I want it all on this page together. So the power at the source is going to be the real part of VS I conjugate. The power at the source is the real part of VS I conjugate. So the power at the source is going to be 11.59 kilo. I don't like this. Okay, let me do it on the board. No, I can't. They can't see if I write on the board. Okay, let me find somewhere to put this. I'm gonna put it up here. So the power at the source is the real part of 1.59 kilo with an angle of, I don't know what the angle is. That's 0, and it's got to be lagging. Then this has to be 60 degrees, right? I'm going with it. We'll see if it works in a minute. Times I conjugate. Maybe I should make it 0. Times 200 was an angle of 60 degrees. Somebody tell me what this is and we'll figure out if it's right. What did you guys get for that value? Because I didn't write this down. Oh, no, it's 2.2. Sorry, this is 2.2 degrees. Sorry, I did have this value. Okay, so 1.5 K with an angle of 2.2 degrees times 200 with an angle of 60 degrees. What's the real part of that? 1.5 K. No, 11.59 K, sorry. It's Friday for me too, sorry guys. 11.59 K with an angle of 2.2 degrees times 200 with an angle of 60 degrees, and then find the real part. What is power at the source? Okay, change it to rectangular form.
I think that'll be 1.08.
Yeah, change it to rectangular form, Sage. So it's 1.08 megawatts. You got to change it to rectangular form and give me the real part. Okay, so 1.08 megawatts. So then our efficiency is going to be 1.08 megawatts, 1 meg divided by 1.08 meg times 100. So we're going to get that the power at the source is 1.08 megawatts. Then the efficiency is going to be the power at the load, which was given as 1 meg, divided by the power at the source, which is 1.08 times 100. So what's our efficiency? 1 divided by 1.08 times 100. 55. Oh, y'all are killing me. I'm not getting any of these numbers. 1 divided by 1.08 times 100. 92.59%. All right, 92. So ideally what you want to do is change the power factor by adding the capacitor bank to improve the efficiency and the voltage regulation. So that means get the voltage regulation under 15% and get the efficiency above 92.59%. Does everyone understand what we're doing? Yes, ma'am.